setting up his group there. He has worked on interesting research problems in 3D computer vision, especially his work on NOx, which is Normalized Object Coordinate for $6 estimation, has been very well received in the community. He did this work, I think, when he was a postdoc at Stanford, with Srinath group. And prior to that, he did his PhD at Max Planck Institute, where he also did some internship at Microsoft. Am I missing something, Srinath? Then you can add.
No.
Yeah. So, I mean, it's a very strong background, I should say, and affiliations he had, and on top of it, he has also now faculty, independent faculty at Brown University, and he's working in very interesting directions with neural fields. Recently, they had a paper on an core sort of survey paper on neural fields, which I think will come into Eurographics. Of course, it might be obsolete by the time it comes publishes because of the way field is moving, but I think it's a quite rich document that you should look at, draft, you should look at to give an idea of what all has been attempted from different perspectives on neural fields. So I think it's over to you, Srinath, to take us through the interesting content here and on object canonicalization, right? And I think this work, as you said, was in collaboration with IIT student, who is soon going to be his PhD student at Brown. So, okay, thank you for being here, and now you can take it over.
Thank you so much, Avinash, for the kind introduction. It's great to be back, although virtually, at IIT. And I remember giving a talk in this very auditorium a couple of years ago. But it's good to be back, and hope you all had a enjoyable experience in the 3D Vision Summer School so far. I think I'm probably the last speaker for today, and I don't know if for the rest of the summer school, but I'll try to keep it interesting, and hopefully you can find something useful out of this talk. All right, so today I'm going to be talking about canonicalization for object-centric 3D scene understanding, and I'm going to describe what I mean by canonicalization, and I'm going to describe all of that in detail. But just to get a high-level overview of what we are trying to do here, given. Let me try to use my pointer here so we can. Just 1 second. All right. So given shapes of 3D objects, so in this case, these are chairs, and we have point clouds that represent chairs. So there's all these little points that you see here on the screen. And we are given these shapes in different orientations. So we are given it in random orientations. So what we want to do is we want to build an artificial intelligence system that can make these chairs upright, right? So I call this colloquially my experiments with making chairs upright. And it turns out that building machine learning systems, building AI systems that can do something like this is very challenging. And I'm going to talk about some of the challenges. I'm going to describe the problem well, and we'll see as we go along in this talk. Okay, so before I begin, I want to start with a quiz. On the top, what you see are 3 chairs that are oriented in a certain way. I'm going to flash 4 more chairs in the bottom, and I want all of you to. I hope I can. Maybe Avinash can, translate for me. But I'm going to show 4 options, and I want you all to tell me which one of the 4 options, which chair below, is in the same orientations as the 3 on top. Okay. All right. Let's try this. I'm going to reveal the options now. Is it A, B, C, or D? You can just,
C, majority C.
Okay, majority C. Awesome. Yeah, you're all right. And it turns out that the task that you just solved is known as a mental rotation task. So the idea here is that given 2 different rotations of the same object, what you're trying to do is you're trying to mentally rotate, right? So you're taking this object, internally trying to rotate it, and you're trying to figure out if these 2 objects represent the same thing, right? And this is called a mental rotation task. It's been widely studied in cognitive science, most notably by Shepard and Metzler in the 1970s, right? Now, it turns out that mental rotation is actually quite important to operate in everyday world, right? So imagine, if you had a scene like this, which had lots of chairs that are toppled, if you want to make these chairs upright, if you want to arrange them properly, then you need to know what a canonical or a standard orientation of the chair is, right? We like to live in environments that have nicely organized things. We have canonical things. Chairs are all upright. Coffee mugs are all upright, and so on and so forth, right? So, as humans, we're all most of us are capable of solving these mental rotation tasks really well. Now, the next challenge for us is if we want to build robots, if we want to build artificial intelligence systems that can operate in this world, we also want them to understand what canonical orientations are supposed to mean, right? So, we need to endow AI systems, endow robots with the capability for understanding what we mean by canonical orientations, what is nicely organized, what is disorganized, and so on and so forth. Now, it turns out that this mental rotation task is a hard problem, right? It's so hard that it's actually used on the internet to differentiate between robots and humans. So, if some of you here might have noticed this on LinkedIn, for instance, if you try to log in after a while, or if you try to log in from a different location, it asks you to solve a CAPTCHA like this, right? And what does this CAPTCHA do? The CAPTCHA asks you to solve an image rotation task. So it presents you an image. Here, in this case, it's kind of like this animal here, or an image of an animal, and it tells you, make the animal look upright by clicking on the rotation arrows here, right? And if you successfully solve it, then the system concludes that you're human. If you can't, then you're a robot, right? And the reason why this is actually used as a CAPTCHA is because mental rotation is so hard that we don't have AI systems that can actually figure out what is upright and what is not upright. Okay. Now, let's come to 3D computer vision, which is the topic of the summer school. And the idea here is we want to have representations, 3D representations of different kinds of shapes. And one way in which we represent 3D shapes is by using a so-called point cloud, right? So what you see here on the left is a bunch of spheres, which are rendered in gray color in this case, right? Each sphere represents one point on the shape, and the collection of all of these spheres constitutes the object shape that you're interested in, right? So that's what you're seeing here on the left here. Now, this representation is very popular in computer vision and computer graphics. And the problem with this representation, though, is there is no notion of a canonical coordinate system, unlike in images. So if you have an image, a 2D image, you're probably familiar with how we represent 2D images, right? So we represent 2D images as a 2D grid, where each location on the grid is called a pixel, and it has a particular value, right, in red, green, blue channels. Now, the 2D images are a 2D representation. So you can represent flat things on it, like 2D things on it, right? But if you want to represent 3D shapes, you need a 3D representation. And point cloud is one of the most common representations that people use for this task, right? Unfortunately, in 2D, we always have a canonical frame of reference, right? We can, because it's a regular grid, we can assign the top left corner to be our origin, and then we can say that the x-axis is in a certain direction, the y-axis is in another direction. Whereas in 3D, if we represent something as a point cloud, there is no clearly defined coordinate system. So we don't have this canonical coordinate system that we can operate with. 3D is also higher dimensional, right? So in 2D, you can, if you want to define a point uniquely, you need its XY position, and you also need an orientation if you have not a point, but a line, for instance, right? So to uniquely define a line, you need to also define an orientation. Whereas in 3D, it's much more higher dimensional. So if you want to describe an object, you need to describe its XYZ position. And you also need to describe its rotation in 3 dimensions, right? So the rotation along the x-axis, y-axis, and the z-axis, right? So the point I want to make here is that representing things in 3D is much harder than representing things in 2D, because there are more degrees of freedom. You don't have this canonical coordinate system, and so on and so forth. Okay. So when we want to understand things in 3D, in machine learning, we are typically interested in data sets so that we can train our machine learning algorithms on annotated, labeled data sets, right? And again, I'm going to draw a comparison here to 2D. where you might have heard of data sets like ImageNet, for instance, right, which is used for image classification. It's a very large data set with 1 million examples. Each image is labeled and so on and so forth, right? Because of the reasons that I described in the previous slide, 3D is higher dimensional, there's no canonical frame and so on. 3D data sets that are used in 3D machine learning, 3D computer vision, have some limitations, right? So the two popular data sets that are used in 3D computer vision are called ShapeNet, which is on the left, and ModelNet 40, which is on the right. These data sets are widely used for research in 3D computer vision. Now, if you notice carefully, you'll see that the ShapeNet data set, I'm showing a bunch of different kind of airplanes, models of airplanes in this data set, right? And notice that all of these airplanes are oriented consistently. So they're all facing the same direction. So it's like, somebody actually neatly arranged them in order, right? And similarly, you'll notice that for ModelNet 40 as well. It seems like, somebody actually cleanly arranged them so that the nose is, in the case of the airplane, the nose is pointing in the front, the tail is pointing in the back, right? So it seems like somebody's done some kind of organization for all of these data sets. It turns out that it's exactly true, right? Somebody actually manually annotated such that all of these 3D models are so-called canonically oriented, right? So they're all oriented consistently such that the nose is facing the front, the tail is facing the back, and so on and so forth. Now, it turns out that this is actually very hard to do, first of all, because people have to manually, canonically orient all of these shapes, which is very time-consuming. And again, because of the degrees of freedom, right? In 2D, you have 3 degrees of freedom, whereas in 3D, you have 6 degrees of freedom, 3 rotations, 3 translations, right? So this makes the task much harder. And this is why this is one of the limitations with existing 3D data sets. Now, okay, you might ask, what's the big deal, right? Maybe we can just spend a lot of money to annotate these data sets and be happy with it and do our 3D computer vision, solve our 3D computer vision tasks, right? Now, it turns out that that's not quite enough because, let's say you want to take a chair from the internet. So you go to some 3D CAD model repository, and then you download a CAD model of cars, for instance, right? And you notice that everybody designs 3D things differently. So some person might want the car to be facing in the x-axis. Somebody else might prefer for the car to be facing along the y-axis, right? So everybody has their own preference for a canonical coordinate system. And on the right, what I'm showing here is an example of a depth image. And depth images are, again, acquired from 3D sensors. So this could be like 3D cameras, it could be LiDAR sensors, right? And what you get from the depth images are also not canonical. So if you observe this bottle here, if you move a little bit and observe the same bottle, you no longer get the same XYZ coordinates. You get completely different XYZ coordinates, right? Because your camera has moved, and therefore the position of this bottle in the image has moved, and each position corresponds to a 3D point, and that has moved as well, right? So the problem with having data sets that are pre-canonicalized is that they cannot help us operate on in the wild data. So in the wild, I mean, data, more 3D models that you acquire on the internet, or 3D data that you acquire from depth sensors and LiDAR sensors and so on. Okay, so I think by this time, I'm setting the stage for being able to do this canonicalization automatically, right? So far we've relied on human annotation, human labels, asking people to manually orient airplanes in the same direction, cars in the same direction. We now want to build a method that can automatically do this. We want to build an AI system that can automatically do this, right? Okay, so before we build anything in computer vision and machine learning, we want to mathematically define it, right? So that's kind of what I'm trying to do in this slide. So mathematically, canonicalization has a very well-defined definition. It's a canonical map is defined as a function that maps from a set X to another set X modulo R, where R is some kind of an equivalence relationship. You don't have to worry too much about this, but very at a high level, the way we can think about this is if X denotes object shapes, so if X is the set of all airplanes, let's say, or the set of all cars, we want to define an equivalence relationship, which is in rotation space. So we want to say, I want to map different rotations of a particular car to a canonical rotation. So that's what we mean by a canonical map here. And it turns out that you can actually do canonicalization for different kinds of object properties. I mean, I took the example of rotation, mental rotation, right? And that's orientation in the list of properties that you can have. But it turns out that you can actually canonicalize for many other things as well. It doesn't just have to be rotation. It can be something abstract as well. Right? It can be what is the canonical shape of a car? Right? I mean, if somebody asks you to sketch a car, everybody is going to draw something that resembles a car because internally we have a canonical representation of what a car looks like, right? So in theory you can canonicalize for many things, but in this talk I'm going to be focusing exclusively on mental rotation or orientation. All right. So I just talked about these data sets, ShapeNet and ModelNet 40, where somebody actually manually annotated these data sets such that all the cars are facing in the same direction, all the airplanes are facing in the same direction. Now, the simplest thing that we can try to do, if you want to automate this process, is to say that let's do supervised canonicalization, right? So we can say that we have the ground truth labels, we have the input shapes, let's try to canonicalize for the input shape using the ground truth labels, right? So this is called supervised canonicalization. And this is very similar to any other supervised machine learning approach that we might take, right? So you give a lot of examples and then ask a machine learning model to predict what the correct canonical orientation must be, right? So that's the first thing. So to kind of describe it a little bit more, let's say in this case we are looking at cameras, right? So given a 3D model of a camera from the internet, right? Or an image, it could also be an image or a point cloud or a partial point cloud, it doesn't matter. What we want to do is we want to output a canonical orientation for this particular camera, right? And that is described by this cube that you see here. So, and this cube is in some kind of canonical orientation, right? And of course, we want this method to be fully supervised. So there is no automated thing here. We showed it's a pattern matching problem, right? So we show lots of examples to a neural network and ask it to predict, given a new example, what should the canonical orientation be? There's been a little bit of work on this. Again, I'm not going to dive into the details here. If you're interested to learn more, I'm happy to take this in the Q&A section. But the limitation with most existing work has been that in order to solve this problem, they've been limited to single instances, meaning you can operate on humans, you can operate on shapes that have a well-defined topology, but they don't generalize to shapes. Like for example, cars. There are different kinds of cars. There are SUVs, there are sedans, there are limousines, right? So there didn't exist a method previously that could operate on these different kinds of shapes. So a couple of years ago, in order to solve this problem, what we did was we proposed this representation that we call normalized object coordinate space. Now, what does this, or NOX for short? So what does NOX do? Given a set of shapes, in this case, we are looking at cameras, and these cameras are from the ShapeNet data set. So they're all canonically oriented. So you can see that the lens is pointing in the same direction. It's like as if someone arranged it, and that's exactly what they did, right? So what we do is we take the ShapeNet canonicalized data, and we map it to a unit cube. So that's the wireframe cube that you see over here, right? So this unit cube is supposed to be a canonical cube, right? And what we do is every single shape that we see, we map it to this canonical cube. So remember this canonical map that I described. So we are doing the same mapping operation there. So we are taking the shape and then we are mapping it to this canonical cube over here. So each corner of this cube has a specific color. So 111 is white, 000 is black, 100 is red, and so on and so forth, right? So what we do is for each shape that we mapped onto this canonical container, we assign a color, unique color to it. Right? So that's the colors that you see here. Now, what this NOX actually tells us is by mapping any object that we see to this canonical unit cube, we essentially canonicalize or standardize for the position, orientation, and size, particularly the orientation, which is what we're talking about in this talk, right? And the XYZ position of the shape is represented by RGB color. Now it's going to become obvious why we are trying to do that in a moment. So why do this mapping, right? Now it turns out that if you can do this mapping, if you can assign a unique color, in the previous slide, as I said, every point of the shape has a unique color, which is defined within this unit cube container on the left, right? So it turns out that if you do something like that, then you can actually directly predict these unique colors from images. So let's say you have an image of a bunch of objects, and you'd like to predict the canonical orientation of each of these objects, right? Now you can actually build a neural network that can solve this task in a fully supervised way, right? So essentially, we build these so-called Knox maps, which allow us to predict these unique colors that I talked about earlier directly from images. And using these unique colors, we can actually figure out what the 3D orientation, the canonical orientation of the objects are. I'm skipping through a lot of details here, but I'm happy to take any questions that you might have during the Q&A. But this is just to demonstrate that it's perfectly possible to solve this canonicalization task in a fully supervised way, right? Yeah, I'll probably skip through this. Yeah, you can use this for different kinds of things. I mean, one application of finding or canonicalizing objects is you can actually figure out what the orientation of objects are in the real world. So given an image like what you see here on the bottom, we can actually figure out what's the box that fits that objects in that particular image, right? And this is useful because, if you have a robot and you want the robot to manipulate objects, you want, first of all, for the robot to know where the object is and what orientation the object is. And this approach allows us to do something like that. Okay, so it turns out that you can also use this for 3D reconstruction. So on the top, you see 5 images of a car seen from different views. And we can actually build a 3D model of this car using this approach that I just talked about. So what we do is, for each image, we predict the Knox coordinates, the colors that I mentioned earlier, and then we aggregate all of that information. Because the colors are in the same canonical space, we can actually do this information aggregation without explicitly finding correspondences between these different images. So it turns out that you can actually build 3D models like what you see here using this supervised canonicalization approach. Okay, now there's a pretty big problem with this approach, right? Here's Jan LeCun, who's one of the leaders in machine learning community, and he often shows this slide that says the revolution will not be supervised. He's French, so he kind of uses that to make a point here, and I quite agree with him, right? The limitation with the method that I've just presented is that it's fully supervised. So we need to show the neural network lots and lots of examples to canonicalize these different objects, and then it canonicalizes it, which is no surprise, right? It's kind of trying to pattern match on different things. But in practice, getting these labels is very hard. Maybe for cars we can do it, but for exotic object categories, like I don't know, like for example this watch that I have here, right? It's very hard to annotate manually for all the different kinds of objects that we might see in the world, right? So that's one of the limitations with this kind of an approach. So as you might have guessed, I'm probably the rest of the talk is going to be about how do we try to do this in a fully unsupervised way or a self-supervised way. And I'm going to present some of our upcoming work on that topic. And we'll talk about some of the details of how we can actually achieve this without using any supervision. But before I move on to that part, any questions so far?
There's one question. I'll just pass it.
Sure, yeah.
So my question is that wouldn't the canonical orientation actually depend on the use case for an object?
Yeah, that's a good question. So canonical orientations are not unique. As humans, we know that chairs, the legs have to face towards the floor, but that doesn't have to be the case for all objects, right? So let's say coffee mug, right? What is a canonical orientation of a coffee mug? You can put the handle on the left or on the right. Different people like it differently. Maybe the right-handed folks prefer it on the right, the left-handed folks on the left, and so on, right? So there is no unique notion of what is canonical. It really depends on your definition. But what we really care about is consistent canonicalization. So if you pick one orientation to be canonical, we want every other instance in that class to be mapped to the same orientation. That's what we care about most of the time.
Actually, a follow-up question on that. So if the orientation actually depends on the task itself this way, wouldn't it actually be more optimal to directly train for the task rather than going to a kind of intermediate canonical interpretation?
This might be true for some tasks. I mean, again, even for tasks, I don't think. Again, I think for most tasks, like for example, let's take object pose estimation, right? Figuring out the position and orientation of objects. Even there, I don't think you care about a specific orientation for whatever, if you want a robot to manipulate coffee mugs. It probably doesn't matter if the coffee mug handle is facing the right or the left. You just want it to be consistent, right? As long as you're consistent, the robot can probably figure it out which side to kind of grab it and so on, right? So even there, I don't know if I fully agree that every task requires one canonical orientation. You probably consistent canonical orientation is probably enough for most tasks. I mean, there's some tasks that require one orientation. For example, if you have a robot that sits on a chair, then the seat has to face in the right way for it to sit on it, right? So that's a different issue. So functional requirements require you to have a more semantic understanding of the underlying shapes. But for most cases, I think it's probably sufficient for you to have a consistent orientation.
Thank you.
Okay, so let's move on to the rest of the talk, where I'm going to be focusing on how do we do this without using any supervision. So the task that we want to solve here is called self-supervised canonicalization. And the idea here is, let's say we have a bunch of input shapes. The rest of the talk, I'm going to be focusing on point clouds, but the ideas are more broadly applicable here. So let's say we have a point cloud, which is represented as the spheres that we talked about earlier, right? Collection of spheres. We're also looking at partial point clouds. So what do we mean by partial point clouds? These are, if you have a depth image of a scene, you don't see the entire object. You only see part of it. Parts of the object are occluded. And that's what I refer to as a partial point cloud. What we want to do is we want to canonicalize for these shapes, right? So given an input shape like the left two that you see here, we want to get these two input shapes, output shapes. And then given the partial shapes, we also want to canonicalize for the partial shapes. So this is the problem that we want to solve. And we want to solve this without using any supervision. So we don't want humans manually labeling these shapes. We don't want to do that. And we want this to work across different instances. So we want this to work on different kinds of chairs, different kinds of cars, and so on and so forth. Right? So the work that I'm going to talk to you about is called Condor, which is short for canonicalization of the 3D pose and partial canonicalizing the 3D pose of partial shapes. And this is work that is actually led by Rahul, who's currently at IIIT. He's a student who graduating from IIIT this year, and he's going to be joining Brown later this year. And this was work that was led by him. It's going to be published at CVPR, which is one of the top conferences for computer vision machine learning work in this kind of problem. All right. So before we get started, I kind of want to define a few things here, right? So the first thing that I want to define is this notion of instance level 3D pose canonicalization. So what do I mean by that? So the three shapes that you're seeing here is the same airplane, right? So it's the same airplane, but in different orientations. The first two are full shapes. So you're seeing the entire airplane, whereas the last shape is only partial. So you're not seeing the front fuselage of this aircraft here. Now, what we mean by instance level 3D pose canonicalization is we want to find this canonical coordinate frame represented by the RGB axes that you see here that is consistent across all of these three shapes. So if you notice here, the green axis is going through the top of the aircraft, and that's the case for all three shapes, as you see here, right? And the red one is going through the bottom, and the blue one is going through the wing, right? So essentially, we are finding a canonical frame of reference that is consistent no matter what orientation the aircraft is. And this is for the same aircraft, right? Now we can extend this notion to this idea of category level 3D post-canonicalization. So what do we mean by that? Category level here means now we are looking at different kinds of aircraft. On the left, you have like a passenger aircraft. In the middle, you have like a fighter aircraft, right? And on the right, you have yet another aircraft that is cut off. So it's only partial. So here, what we mean by category level 3D post-canonicalization is for these different aircraft, we find a consistent orientation. So in other words, the green is going through the top of the fuselage, the red is going through the bottom of the fuselage, right? So that's what we mean by category level 3D post-canonicalization. So what we want to build is we want to build an AI system, a neural network that can actually find this category level 3D post coordinate frame, given different kinds of shapes. Okay. So it turns out that in order for us to build neural networks that can solve this problem, that can learn to canonicalize in a fully self-supervised way, we need a few ingredients. The first ingredient that we need is what is known as permutation equivalence. And I'm going to describe what I mean by that. Now, we talked about point cloud, right? Point clouds are one data structure that is used to describe 3D shapes. And it's very simple to describe a point cloud. So, if you were to program something where you use a point cloud for a task, the point cloud would actually be described in computers as XYZ coordinates, and you'd have a bunch of these XYZ coordinates. So that's what you see here on the left here, right? So you have 0.33, 0.36, 0.43. That's just represents the XYZ coordinate of one point in this shape. And you have rows and rows of those points. Let's say we have 1024 points, right? So this matrix is 1024 rows and 3 columns. And this matrix represents the shape that you see here on the top. Okay, so that's how we, it's very easy. It's nothing complicated, right? So if we want to represent 3D shapes within computers, we just describe the XYZ coordinates. Now, if you want to build a neural network that processes this kind of XYZ coordinate, similar to a 2D image, right? So if you have an image, you have a convolutional neural network that takes the pixel value and then processes it somehow, right? So in this case, we have the XYZ values, and we have rows of these XYZ values, and then we use a neural network. Typically, we don't use a convolutional neural network. We use a fully connected neural network or a multi-layer perceptron to process that information, to extract some kind of features, which are shown in the colored bars here, that's useful for some kind of downstream task. Now, there's a bit of a problem here. And the problem is that if we permute the rows, the XYZ coordinates, like this. So we've just changed the order of the rows of the XYZ coordinates. Now, that doesn't change the shape at all. The shape still looks exactly the same. You're just describing the points in a different order, right? So instead of saying going from the top left, XYZ, describing each point from the top left, you're just describing it in some other order, right? Now, the problem with this is neural networks, if you have these XYZ, the order of the rows shuffled, neural networks end up extracting features that are completely different. So as far as the neural network is concerned, it's now a completely different shape, right? So we want to build a neural network architecture that is aware of this shuffling of the rows. In other words, we want to build a neural network that shuffles the rows or shuffles the features depending on how the input rows are shuffled. And this property is called permutation equivalence. What I mean by that is if the rows of the input shape are permuted, the output features are also permuted in the same way. So this property is called in mathematics as the equivariance property. So that's something that we need if we want to build a system that can canonicalize. The second thing that we need is this notion of rotation equivariance, similar to permutation equivariance. So let's say we have a shape, which you see on the bottom here, which is a rotated version of the shape on the top. So it's just rotated by 90 degrees. Now, if we want our network to be rotation equivariant, we want the output features to also be rotated by 90 degrees. Okay, so very similar to the permutation equivariant case. Finally, we have the notion of translation equivariance. So let's say you extract features. The features are shown very abstractly as this yellow and red bar on the top that you extract from your neural network, right? So given a shape like this, you might extract a feature that abstractly looks like what you see on the top. But if you translate that shape to a different location, we want the features to also translate in the same way. And by the way, this is a property that you already have in 2D convolutional neural networks. So if you're trying to detect a dog in an image, no matter where the dog is on the image, your 2D CNN is able to detect that dog, right? And the property that enables 2D convolutional neural networks to do that is called the translation equivariant property. We also need that for figuring out the 3D to mentally rotate shapes. Okay, so in order to build a neural network that has all these three properties, permutation equivariance, translation equivariance, rotation equivariance, we actually use something called tensor field networks. I'm not going to go into the details of this network, but I just want to point out here that this particular neural network has the three properties that we talked about earlier. So, it's equivariant to permutation, it's equivariant to 3D rotation, and it's equivariant to translation. And this is a network that is used for lots of different tasks, and we kind of build on top of this particular network. Of course, there's many other alternative architectures that you could adopt. One example is capsule networks. You might have heard of this. Capsule networks are an attempt to make neural networks equivariant to rotation, permutation, translation, and so on. There's also spherical convolutional neural networks. There's steerable convolutional neural networks and vector neurons. We're not going to go into any of the details here, but just for your reference, if you'd like to read a little bit more, this is probably where you should be looking at. Okay, so let's put all of this together. So we want to build a neural network architecture that can canonicalize for 3D shapes by using these three properties, the three ingredients that I talked about: permutation equivariance, translation equivariance, rotation equivarience. So what we're going to do is we're going to first of all extract some features from the tensor field networks that I talked about earlier. And we know that TFNs, the features that we get are equivariant to rotation, translation, and permutation, and so on. Right? So if you jumble the rows of the point cloud, the features are also shuffled appropriately. We then use a multi-layer perceptron, just fully connected neural network, to extract some kind of a canonical rotation. So that's the canonical rotation that we're looking for. Now, to make sure that we actually learn something useful for a different shape, I mean, earlier you were looking at a passenger aircraft. Now you're looking at a fighter aircraft. And we want to make sure that the canonical orientation that we get for the fighter aircraft is the same as the one that we get for the passenger aircraft. Right? So in order to ensure that, we have an additional branch for this neural network architecture. And what this branch does, I mean, again, I'm not going to go into too many details here, but at a high level, it uses something called spherical harmonics. And it uses some interesting properties of the spherical harmonic functions that enables us to treat the spherical harmonics coefficients as coefficients of the features that we extracted from the tensor field networks. There's some very interesting mathematics behind this that I'm probably not going to go into that right now. I'm happy to talk about this later. But anyway, we use this useful mathematical properties in order to make sure that different instances, different kinds of airplanes, we can canonicalize them consistently, even if the shapes are slightly different. We use a loss function, which essentially ensures that when we reconstruct the shape using a multi-layer perceptron, which is very similar to the input shape itself. So that's just some regularization loss functions that we use for this. So we refer to this architecture in the blue box as Condor, or canonicalization of 3D pose for partial shapes. This, of course, the architecture that I showed about is mostly for full shapes. So if you have the complete shape of the airplane, then this architecture works fine. It turns out that we can actually also handle partial shapes. So let's say you have on the top you have a full version of the fighter aircraft, and on the bottom you have a partial version. So somebody cut off the shape of that particular aircraft, right? Now it turns out that you can actually use Condor for canonicalizing even these partial shapes. So you essentially extract a canonical orientation for both of these shapes, and you ensure some kind of a loss that makes sure that the partial version of the full shape aligns with the partial shape canonicalized. Right? So I'm not going to go into too many details here, but essentially, you can canonicalize for the partial shapes as well. Okay. All right. Now, another interesting discovery that we made when we were kind of building this neural network architecture is that we're not just limited to finding the canonical orientation, we can actually even segment the shape into parts, consistent parts, right? And we refer to this as unsupervised cosegmentation. So what do we mean by that? Essentially, if you have different airplanes, we can divide it into smaller parts. So you see blue, red, yellow, green, and so on here. That the parts are consistent across different airplane instances, right? So the blue part is always the right wing, the brown is always the left wing, the yellow is the middle portion of the wing, right? So it turns out that our method can actually consistently find these parts as well, and we refer to this as cosegmentation. Again, there's no supervision here, right? So this is like saying, without using any supervision, we discover what are the parts of the shape that we are looking at, which is useful for several kinds of stuff. For example, if you have a coffee mug and if you want a robot to grab that coffee mug by the handle, our method can actually give you where the handle is without anybody actually telling it where the handle is. Okay, so I'm actually going to move on to results here. I mean, we defined some metrics because we need to demonstrate that our method works well, right? And one way to do that is to show numbers, to quantitatively show that we are doing a good job, right? So we define a few metrics to enable us to do that. I'm not going to go into the details here, but yeah, essentially these metrics are meant for analyzing different properties of our method. Okay, so let's look at full shapes. Now, what you see on the top here, the gray chairs that you see here, are the input to our neural network. We can first of all apply some very simple canonicalization technique. Right? The simplest thing that you can do is PCA, or principal components analysis, right? And what PCA does is it finds, using eigenvalue decomposition, it finds what are the three major axes of the shapes that you're interested in. And PCA does okay. It's better than we expected, but that's the yellow shapes that you see here. But still there's no consistency here. We also compare against some other methods. On the top, you see canonical capsules, which use capsule networks. On the bottom, you see compass, which uses spherical CNNs. And we compare against these methods. Well, these are the results from these methods. As you can see, they are better than the input, but still not fully consistent. And on the bottom is our method, right? So the method that I just described, Condor, it can actually canonicalize for the shape of chairs pretty consistently. And definitely doing a much better job than the other methods. I also have some quantitative numbers here that I'm not going to go into, but the surprising result here is that PCA is not too bad. Something as simple as eigenvalue decomposition, which you might have learned in high school, or you might be learning it in your first year of university. PCA is actually surprisingly good, right? You can use this for canonicalizing to a reasonable level. But if you want better performance, then you have to use methods like what we propose. So here's a video for partial shapes. So what I mean by that is the input to our method is not the entire shape, but it's only half a slice of it, right? As we show here, our method is actually able to canonicalize for partial shapes as well. So you see all the airplanes are consistently oriented, the chairs and the lamps and tables and so on, right? And again, we have quantitative results for that. I think our method is much better than any other method out there. So here's a few more examples. What you see on the left are the input uncanonicalized shapes. What you see on the right is the canonicalization that our method is able to extract. And you can see that all the airplanes look consistently oriented. The tables, chairs, they're all consistently oriented. And same thing for partial shapes. On the left, that's the input to our neural network. On the right is the reconstruction. We're showing the partial part of the invisible parts of the shape as well, just for visualization. But that's the network does not see the gray parts that you have over here. Okay. I mean, of course, our method fails in some cases as well, right? So here we show some failure cases. Failures are most often a result of symmetry. If you have something like a table has a vertical axis of symmetry. And our method confuses. It doesn't know what is left and what is right and so on, right? Thin structures like this lamp that you see here are also hard to capture from our method. And also when you cut off too much of the object. So here we've cut off most of the bottom half of the shape here. So we find it a little bit hard to canonicalize for that. Okay, so in the beginning I talked about operating on in the wild shapes. So you go download a 3D model, or you have a depth map or a LiDAR scan of a scene. It turns out that our method can operate on this kind of in the wild data, right? So if you take data from the internet, you can actually use our method to canonicalize any shapes that you might see on the internet, and canonicalize it into the overall canonicalization that we achieve here. Okay, so if you want to play around with this method, code and data sets are publicly available. You can go to this GitHub link here. We have code in both PyTorch as well as in TensorFlow. So you're all welcome to go online and then try this method if you're interested. Now, just to summarize, I was talking to a family member about this, and they asked me a question. Right? They asked me a question: did you really spend 6 months trying to rotate some chairs? That was the question that they asked me. And it's actually a fair question to ask, right? And it tells us how hard some of these 3D computer vision tasks are and how far away we are from solving them, right? Now, if you go by the popular press, people are talking about whether artificial intelligence systems are going to take over the world, whether they're conscious and things like that. But it turns out that AI systems are pretty dumb, right? Even solving something like canonicalizing chairs, the shape of chairs, tends to be a very, very hard problem. And we did spend 6 months trying to solve this. We have a solution, but we're not claiming that the solution is conscious or is going to take over the world. And of course, this has wide applications, right? So the fact that you can compare different chairs, different shapes, and conclude that they or map it to some kind of canonical frame of reference gives you very, very powerful capabilities for robotics, where you want to operate on scenes or scene understanding systems and so on and so forth. So this has really wide applications in lots of different domains. So future work, we are currently, in fact, Rahul is currently trying to extend this method to articulating shapes. So in this case, we are showing laptops, right? So if laptop is an articulating shape, it can move. It has a hinge that can hinge. It can move, right? So we are trying to canonicalize for moving things like that as well, like articulating shapes, right? We're also building. I believe you may have been introduced these neural fields or implicit neural networks in the summer school before. We're also trying to build these neural fields that are equivariant, that have these equivariance properties, that have these canonicalization properties, so that we can kind of build more powerful neural fields, essentially. And talking about neural fields, I also wanted to briefly mention some recent work that is upcoming from our lab. Neural fields are essentially these neural networks that that are capable of solving visual computing problems that can be formulated as a field. What do we mean by a field? It's kind of similar to a gravitational field or an electromagnetic field, except that you're not modeling gravitation or electromagnetism. You're modeling things like shape of the object or appearance of the object, the radiance of an object, and so on and so forth. So there's a lot of work that's being done in this area. So we've written a review paper about this, which reviews over 300 neural field papers. You can go to neuralfields.cs.brown.edu. That website has the review paper as well as a searchable database. So you can actually search through different kinds of papers and so on. So you're welcome to go try this if you like. And this was work that appeared at Eurographics last month. We are also going to have a CVPR tutorial next month on this. Okay, so with that, I'd like to thank my students at Brown, our funding agencies, and I also just wanted to point out here that we're always looking for motivated students and postdocs. So if you're interested in these kinds of topics that I just talked about, please reach out to me. And yeah, thank you for listening, and I'm happy to take any questions.
Yeah, we have one question. Hello. So when you're using the spherical harmonics, is there a loss of information by trying to learn the spherical harmonics, like putting the input point cloud into the spherical harmonic learning?
Yeah, loss of information. Good question. So it turns out that the information with 3D shapes is really the geometry, the details of the geometry, right? Now it turns out that when we do this spherical harmonics approximation, we can leave out some of these details, and that's exactly what we do. For canonicalization, you don't need a lot of details. You need some details, yes, but you don't need a lot of details. But for the segmentation, we observed that using lots of spherical harmonics coefficients, meaning a better approximation, is actually better. So we can segment out the shape of the object much better. Yeah, to answer your question, for canonicalization, loss of details doesn't seem to be a big issue, but for segmentation, you probably still need a lot more details.
So my second question was going to be on segmentation. So how is it working? Like, we do not have any information on which part to segment, and how is self-supervision helping us in that? Yeah,
so let me maybe try to go back to this slide. Issue, but for segmentation, you probably still need a lot of details. I'm sorry, I can't hear you very well.
So how is it working? We do not have any information on which part to segment, and how is self-supervision helping us in that?
Yeah, so let me maybe try to go back to this slide. Issue, but for segmentation, you probably still need a lot. Yeah, so what's going on here is, your question is, how is it consistent, right? How can we really find this without any supervision? Now, it turns out that in order to canonicalize and in order to find this consistent parts, what you need to solve is exactly the same thing. You essentially need to give unique labels to different parts of your shape. So if you have an aircraft here, you want to give a unique name to the right part, the right wing versus the left wing, and so on and so forth, right? And that's exactly what the method ends up doing. So it gives unique names to each of the shapes in terms of the features. So that's what really helps when you give each part of the shape a unique name. That gives you the capability to segment out that part consistently as well.
Can you hear me?
Yes, I can hear you now.
There was some technical glitch. I think there was a lot of echo and repetition happening. So I am not sure if you answer. Okay. Anyone else want to share to us? Some technical thing happened in that I don't know, or repetitions.
Yeah, it seemed like the live stream was also running with a bit of a delay, so I could actually hear myself. Yes, yeah. Yes, I can hear.
There was some technical doing I think I think please stop the live. I'm not sure if it is causing the echo and yeah, now it's gone.
Okay, good. Yeah.
Because that is running delayed, actually delayed, right? So
Yes, it's probably about 10-20 seconds behind. Yes.
that's okay.
Right. So you mentioned about the canonical. Can you shed some light on that? Like how can we canonize the? Hello.
So I don't know if someone's asking a question. I can't hear very well.
Okay, so I wanted to know, you mentioned in your slides that we came with depth map canonicalization. So can you shed some more light on that? How can that be done? How can we use it?
I'm so sorry. I cannot understand.
The question I'll repeat. Am I audible?
Yes, I can hear you.
Yeah, the question. Yeah, the question is on depth map canonicalization. How do we do that? And how is it useful?
Right. So depth. Yeah, good question. So I didn't get a chance to talk about this in a lot of detail. But essentially, the idea here is with depth map canonicalization is that depth maps are partial point clouds, right? So here we are showing an example of partial shapes. When you're looking at a depth map, you're only looking at the visible parts of your shape, right? So you essentially end up getting like half the shape, roughly, right? And this is what we are showing here. So you operate on partial point clouds. I mean, in these tests, we didn't use depth maps. We use sliced shapes. So we take a shape and we slice it into half, and then we do it in random orientations. Whereas in a depth map, you have something similar as well, right? So you see only the front-facing part of the shape. So it's no different from canonicalizing the partial shapes that you see here on this slide.
Okay. Any other question, guys? No? Okay. I would like to thank speaker. So Srinath, thanks for being with us. I think it must be early morning for you. So it was an interesting talk, and I hope students got a lot of exposure of problem solving, which is very practical and important. Yeah, with this, I think we conclude this talk. So thanks again for joining, and I have sent you some e-gift from our site, Amazon coupons for basically your efforts to join here. And I hope we'll continue with this kind of events in future. There'll be a small reflective session with where Mr. Jawahar and PJN will also be here in the next 10 minutes in this room. So all of you, all audience should stay here is what my request. So thank you, Srinath. Yeah, I think we can stop.
Thank you,
here.
everyone. Yeah. Very interesting question.